Hi, my name is Henry Segerman. These are hyperbolic honeycombs. This is joint work with Royce Nelson. To be precise, this is the 435 H3 honeycomb, H3 being three-dimensional hyperbolic space. This is the 534 H3 honeycomb, and this one is the 633 H3 honeycomb. So what do these numbers mean? So these are the Schlafly symbols for these tilings. So what's a Schlafly symbol? So ignore the fact that this is a tetrahedron for a second and just think about the triangle. The triangle has Schlafly symbol 3, which is it's a regular polygon with 3 sides. Square has Schlafly symbol 4, and the pentagon has Schlafly symbol 5. Okay, so now take a bunch of triangles and make a tetrahedron. Tetrahedron has Schlafly symbol 3, 3. So the first 3 says it's made out of triangles, and the second 3 says that there are 3 triangles that meet at each vertex. And for a cube, this has Schlafly symbol 4, 3, because it's made out of squares, and 3 of them meet at a vertex. And then you go one further, so for example, the hypercube has Schlafly symbol 4, 3, 3. So the first 2 say it's made out of cubes, and then the third one, 3, says that you arrange 3 cubes around each edge. So there's this edge here, there's the 1 cube in the middle, and then 1 cube over here, and 1 cube over here, and those 3 are arranged around this edge here. So sometimes when you give a Schlafly symbol, you have a tiling of the sphere. So in a way, the cube is a tiling of the two-dimensional sphere, and the hypercube is a tiling of the three-dimensional sphere. But sometimes you get tilings of Euclidean space or tilings of hyperbolic space. So that's what's going on here. This is Schlafly symbol 435. So 4,3 says that it's made out of lots of little cubes, and then 5 says that you arrange 5 of those cubes around each edge. So let's find, so let's look down this edge here, and you can see that there are 5 cubes arranged around that edge, so you get 435. And this one is 534, so 5,3 says that it's made out of dodecahedra, 5 pentagons, and then 3 pentagons, so you have 3 pentagons around each vertex. And then this is 534, we should see 4 dodecahedra arranged around each edge. So let's look down this edge here, and you can see that there are 4 dodecahedra arranged around that edge. And then finally, this is 633. Well, so what's 6,3? 6,3 says take regular hexagons and arrange 3 of them around each vertex, and so you don't get a polyhedron, you get a tiling of the Euclidean plane. Okay, so 633, I'm supposed to arrange 3 tilings of the Euclidean plane around each edge, which is a little difficult to imagine how you would do it until you see it, and well, here it is. So here's a tiling of the Euclidean plane, here's another tiling of the Euclidean plane, and here is a third tiling of the Euclidean plane, and they meet at this edge here. So you can look down that edge there, you can see that there are 3 of these tilings of the Euclidean plane arranged around that edge. So that's 633. So this one was 435 and this one was 534, and you'll notice that the Schlafly symbols are, if you reverse one you get the other, and that corresponds to these being dual tilings. This actually holds true for the polyhedra as well, so the cube is 4, 3, 4 squares, and then 3 squares around each vertex. The octahedron is 3, 4. 3 meaning triangles, 4 meaning that there are 4 triangles arranged around each vertex, and the octahedron and the cube are dual to each other, of course. And so the same thing happens here. Each vertex of this one corresponds to a cell, in this case a cube of this one, and vice versa. And so you could arrange these two in space at the same time, and the edges of this one would pass through the faces of this one, and vice versa. So these two are dual to each other. So what about 633? So the reverse of 633 is 336. And just so happens that I have such a tiling of H3, so that this is the regular tiling of H3. So this is 336, the reverse of 633. So 33 says that's a tetrahedron, three triangles around each vertex. And then it's a little harder to see on this one that there are in fact 6 tetrahedra arranged around each edge, but that is the case. And so these two are also dual to each other, and you could in principle arrange them so this vertex is actually an ideal vertex on the boundary of H3, is in the same place as well, this gap. Really these hexagons should continue tiling, getting smaller and smaller as you get out towards the boundary of H3. So these are hyperbolic honeycombs.